Hello, everyone. Is the Prophet Michael David, aka Aries, and it has been a while, a couple months, I think. So, why today? Well, today is Michaelmas, so I'm going to be doing my last two videos. This is my first tie. There's going to be the fan favorite tie for the Riemann hypothesis, but today I'm going to do a video about perfect numbers or how I solved it. Okay, so again, I admit it's been a while and I'm a little bit out of practice, so bear with me. But I'm going to try to keep to the same format that I did with the last two videos, which were twin prime conjecture and then college conjecture. Again, they were a couple months ago. But so here we go. Here is the video that you should watch before you watch the rest of this video. Okay, so again, that Veritism video of the perfect numbers is what you should watch first before the rest of this. And this second screenshot is just of all the files that I used in the creation of this video. Again, like I did in the first two videos. Okay, so now into the perfect number conjectures. There's actually two of them if you watch the videos. You have to prove that there are an infinite amount of perfect numbers, and you have to prove that there are no odd perfect numbers. So again, shout out to the person that watched a lot of my first perfect numbers video. There was somebody was spamming it and everything. This is my initial um, theory solution, symmetry solution. You could call it conjecture, but it's based on pure symmetry, which all perfect numbers have to have. And here it is again. So again, as I've explained in a previous video, it's a symmetry argument based on primes themselves, that they all have to fall on those three mod lines because of many things, of course, and of course because they all have to satisfy their position on those mod lines. The nth position has to be always in 2, 3, 6, because for the same reason that the first perfect number is 6, there's a real famous equation: 1 over a plus 1 over b plus 1 over c equals 1. What is a, b, and c? There's only three numbers that can be, and it's 2, 3, and 6. So, but from here on out, I'm going to explain it in other dimensions, 3 dimensions, 2 dimensions, so that you guys can see that, yeah, I pretty much just smashed this in a whole bunch of different ways. Okay, that is, of course, a screenshot of the first 8 perfect numbers and the Mersenne primes that make those perfect numbers. And again, if you watch the video and you know about this stuff, um, you know, it's the Mersenne, they find the Mersenne primes first, and then they know those are perfect numbers because, again, of the Veritism video and everything. But that's where we start. That's where I started. And I found out that the best way to look at them was actually in the Veritism video, that think of them as a stack of cubes. Okay, so that video or that screenshot is from the Veritism video that you should have watched, but that's the best way to think about perfect numbers is a stack of cubes, a stack of odd cubes, because to get an even number, you need two odds. Odd plus odd equals even, odd plus odd equals even. So they have to be an even stack of odd cubes to create a perfect number. But from that, you can deconstruct it and then construct it in a different way to show what it has to be. So I made a spreadsheet, of if I know they're just stacks of even amounts of odd cubes, then I just made a spreadsheet and then highlighted the ones that are actually Mersenne primes. And we're getting to the reason, although you can see it if you look at it, why they become rarer and rarer. And here, this next screenshot is just zoomed out so you can see how far I went to get the actual Mersenne primes and perfect numbers. Okay, so now I'm going to show you about the transformation thing that I just mentioned about a minute earlier, where you can transform that stack of stack of cubes, uh, and transform it into like an old school skyscraper. And so the next three slides I'll show you is how the first two, three, and four. So not six as the perfect number because that's the even one out, but the next ones, 28, 496, and 8128, how you can transform them from the tower of stacked cubes into like the real thin, tall skyscraper, and why that makes a difference, or why that shows it is a perfect number. So now, logically speaking, like you can see that, right? They're towers of cubes. We're doing, I didn't have 3 dimensions drawing thing. I just did it on my spreadsheet and everything. But they are a set of 3 dimensional cubes, which you can deconstruct and turn into like the skyscraper that has a square base and everything. So, and if you look at the first slide too, where I did all the dragging downs and where, you know, the spreadsheet, you can see that the Mersenne primes only happen at the longest points of the spreadsheets, and that's the transformation between 3 dimensions and 2 dimensions. And the thing that makes a perfect number, can you have a stack of an even stack of cubes that are not a perfect number? Yeah, most of them aren't. So what makes the transformation into the old school skyscraper uh, a, a perfect number? It's because that skyscraper is exactly prime number floors tall. If that number isn't a prime number, then it's the sigma function value is going to be over 2. Again, the skyscraper has to be prime stories tall. So 27, 127, that's what the Mersenne prime is. And that's the best way I can describe it. Okay, and another way to look at it in two dimensions for the perfect number A128, as you can see, it's just a prime number times a bunch of twos. That's all they are. It's just one prime number times a bunch of twos. So the prime number sets the height of the skyscraper, and the bunch of twos forms the base and then fills everything else in the 3 dimensional model. It's just one prime number and a bunch of twos. And they have to equal sigma value exactly 2.0. But then finally, I found out the best way to describe perfect numbers to you, and that is that all perfect numbers are a finite summation of reciprocals of natural numbers. So basically, all that means is reciprocals 1 over. And I found out this when I saw this. So as you can see for 6, 28, and all their perfect numbers is that the sum of the reciprocals of their divisors equals 2. The kicker that I noticed was that 1 doesn't have a divisor or it doesn't have a reciprocal. 1 over 1 is just 1. 1 doesn't have any more divisory capability than it does multiplication ability. That's why mathematicians don't consider 1 a prime number, because it messes up their fundamental theory of arithmetic. But they have no problem using it as a divisor when it makes the numbers better. But 1 isn't actually a divisor. And so if 1 is just 1, then you take it to the other side of the equation, and 2 minus 1 is just 1. And so I realized that the reciprocals of the divisors of all perfect numbers, except for 1, because you don't consider 1 a divisor, is equal to exactly 1, which brings you into the realm of sum of infinite series and sum of finite series as well. And perfect numbers in this context are just a series of reciprocals, finite series of reciprocals that happen to equal 1. So, and we're getting to the end of this video, I promise. Riemann hypothesis next. But so I broke down the are there any odd prime numbers question into a question that is totally different. Are there any combinations of odd reciprocals that can result in a whole number, can equal 1? Or any whole number, because then you can just divide it by that and everything. And the answer is no, you can't. But the way I did it was I went to the spreadsheet again, and I showed this before, but I'm going to explain now. I just did, okay, well, I know eventually, 1/3 plus 1/5 plus 1/7, because I got to use all odd numbers, and I have to have an odd number of them for, you guys can figure it out. But to make an odd prime or an odd perfect number, like how many, and they're all just subsets of like the harmonic series, so they're all divergent. Is there any combination of odd reciprocals, so odd fractions, but it's 1 over because it has to be a reciprocal, that can make a whole number 1 or a whole number? And so this is the spreadsheets I did to show that it can't happen. So if you look at those 4 screenshots, you can see what I actually tried to do was I just did the odd fractions, either 1/3 plus 1/5 plus 1/7, happens to make an odd perfect number. And once I got up to, I tried to get it as close to 1 as possible, because that's the geometric summation we're trying to make. And it was always over or under, hence the colors. You can look that up. You guys know my coloring situation by now anyway. And then from there, zoomed out, you can see I did a lot of data points to do that. And then the next one was the fluctuations. Those were how above or below they were from 1. And you can see they're getting closer and closer to 1. But it's, again, it's a wave-like, it's not asymptotic, but it's wave-like that eventually will solidify on a single value, but not until infinity. And the last one, you can see that in the value, that it's getting closer and closer and closer to 1, but it never is. The spoiler to this is that you can't do it. Yours gonna, the last, you can put like 1/3, 1/5, 1/7, 1/9, up to a certain point. But the last term, to make it an actual whole number, is always going to be a fraction. It's never going to be a reciprocal. It's never going to be 1 over. And so, and also I found out that some of these other terms also seem to converge on 2 pi or whatever. And so I'm going to show you those screenshots right now. Okay, so if you're really into nerd into this, those last 3 are, and you can tell by the spreadsheet and everything, they're just graphs of different equations that I found using, again, just the odd reciprocals of primes added together that seem to converge, or at least are asymptotic to both pi and 2 pi in their own way. So take that as you would. The asymptotic one looks like, yeah, it's asymptotic to pi, the middle one. So lastly, yeah, there are not any odd perfect numbers because of everything, the geometrical distribution, the symmetry, everything that I've told you up to now. The other thing that solve perfect numbers conjecture is, are there an infinite amount of them? And the answer is yes as well. And this is how it's related to the Kautz conjecture. Okay, lastly, before I sign off on this video, For those of you that watched my Collatz conjecture video, so in that slide, 731, 127, 8, 191, those are all Mersenne primes. The gold ones are Mersenne primes. The reason why I have it labeled possible M primes, Mersenne primes, is because the ones like 511 aren't, for reasons we've already discussed. But then you can see as you pull down, log 2m1 is just like doing backwards the 2 to the n minus 1 to find out what the actual 2 to the prime is. And then the 1 mod 6 transformation is, or 1 mod 4 transformations and everything are, you can see how when you keep dividing those numbers by that they become the magic numbers in my Collatz video. 1, 5, 21, 85, 341, magic numbers. Those numbers which, if you pick them or any time that they get hit in a Collatz game, the number you automatically win. It automatically goes, slides, shoots and ladders. You got ladders. It goes all the way down to 1. And so, are there an infinite amount of perfect numbers? AK, are there a perfect amount of Mersenne primes? Yeah, because they are a subset of the magic numbers in the Collatz game. You're going to get an infinite amount of magic numbers, up to infinity in Collatz games, and not all of them will be associated with a perfect number, but every once in a while, they will. And for the same reason, they get rare and rare. And the ultimate end to this, TED Talk about perfect numbers and the whole skyscraper thing. And you can see how the possible M primes get really, really big, really, really fast. It's just a question of, the stack, the Tower of Babel looking thing, the stack of cubes, whether that transformed size skyscraper is a prime number. And as primes get rare and rare and rare as you go up in larger numbers, that's why numbers that are millions of digits long, why that specific skyscraper, it's probably not going to be prime level tall. It'll be divisible by some other number other than a single prime. And that's the game. So the numbers that are possible to be able to be these numbers go up exponentially. And then also the primes get rarer and rarer and rarer. And the combination of those two effects is why perfect numbers go up so quickly, why we've only found every 52 of them ever, and why there are an infinite amount of them, but they're all even because they have to serve that geometric summation. And if you try to do that geometric summation with only odd numbers, you're never going to get a whole number, ever. That's like the definition of a divergent series, or at least the best definition of one. So I know this video is kind of long-winded today. I know I'm a little bit out of practice. I hope you guys learned a lot. I'm going to put on the new tie for the Riemann hypothesis and do that one right after this video. But I love you all very much. You have a wonderful day. 2 rules. Rule number 1, do not touch other people without their consent, aka do not hurt each other. And rule number 2, try not to lie. It's all about honesty. Lies are a tick down. So I will talk to you all here in like 10 minutes.